Hey, this is Srini and from As We Go. I'm with Satinder Paul Singh. We're presenting this at ORConf Munich, Germany. It's unfortunate that I won't be able to make it to the event, but Satinder would do a great job doing that live on the show. I'm reaching out to you via the social media platform, trying to share the way I see this technology, where it's started, how it's going, and why it's so needed. So let's get started. So this is again ORConf, which is the premier open source digital design conference that gets scheduled across the globe. And we were glad to do a similar one at a Latch Up event in the US earlier this year at Santa Barbara. And this time we are in Munich. So we're going to talk about system verilog test bench linting with open source tools. And it's all completely Python based. It's completely customizable to what you want and do the way you would like it. Again, my co-author is Satinder Paul Singh. He's part of Cognate. He's the Europe CTO, and he can be reached over there. And that's my email ID, svenkat@asvigo.com. Asvigo is a UK-based startup. So to begin with, why do we even care? Why test bench linting to begin with? As has been demoed in various software and hardware design projects, the shift left is achievable if you do find issues as early as you can. Could be the design, the best, and then static analysis during the development phase, and then testing, could be your unit testing, integration testing, etc. And then finally, of course, the deployment in case of software, and then in case of hardware, you go through a lot more painful post-silicon debug. Right. So essentially in all this, what we want to say is we want to find bugs as early as possible. And so what are the opportunities in verification to do all this, right? To begin with, again, I'm going to focus only on the test bench part, but of course, RTL linting has been there in the industry for a long time, and a lot of customers use it. And the good thing is today, open source RTL linting is also possible quite a bit. Very much the same PySlint can be used to begin with. Okay, now, system verilog test benches provide you ample opportunities to go wrong and hence introduce bugs in your test benches, which would eventually turn into issues with your design not being tested properly, right? So you do want to make sure your system verilog test benches, specifically the class-based test benches, are linted well and good. Could have your own custom rules or the standard set of rules that are available. So UVM adds another whole layer on top, and you could easily go sideways with your UVM code if not done correctly. There are best practices that you want to adhere to. Same thing with assertions. In assertions, you have two forms of it. One is for the simulation part, other is for the formal verification. So you may have a subset of rules that would say that these assertion syntax or these constructs you want to stick to if you are going with formal verification, such as formal property verification. Right. Same thing for system verilog VIPs. You may want to know whether it's compatible with acceleration, emulation. Your specific EDA vendors could come and tell you that these rules are to be followed if you want to use this specific emulation platform with your system verilog test benches. Again, so far there has not been easy way of adding these rules and checking whether your VIP or VIP is compatible with the acceleration, emulation, etc. And today it's all possible now. So how do we achieve in open source domain? So essentially it's a new paradigm, but the concept has been proven in RTL side. The code analysis approaches are changing today. The way we've been thinking about it in the past, you needed complicated and more expensive tools to do all this. Today, good thing is there are many open source parsers becoming available. Some of them I listed there. Slang is C++ based. Variable is from Google, again C++ based. There's some Python interface, but not so popular yet. SPLint is another option. I believe it has a Rust interface. I particularly haven't tried too much of it. And then of course we use a lot on PySlint. We built something on top of PySlint. We call it PySlint. Right, again, it's all open source. It's on the GitHub. Please go and take a look. It provides flexibility in customization options, which would essentially mean that you can build your own linters, which is what we did, right? And we allow customers to add their own things, and we also allow the APIs to be customizable. so that if you like what you see it, go and take it. Don't pay anybody any cost. Use it for yourself, right? You can do what you want commercially. But in case you wanted customizations, of course, you can build on top of it. Again, as I mentioned, there's variable other options, SVLint and then PySlint is what we do. Right? Again, just a nice note that always code as if the guy who ends up maintaining your code would be a violent psychopath who knows where you live. So just scaring you a bit to say that your code shall better look clean and maintainable. So how do we approach it in PySlint? PySlint is the name that we came up with on top of PySlang. So it's built on top of PySlang, Python-based rules, which is what I love about it. So on the right-hand side, you see a screenshot of how the devs look. Very, very simple and straightforward. If you understand the data object model of Verilog, starting with the VPI, PLI stuff, it's something very similar in the class-based approach. Right? You have a class, the class is declared, the class has many methods, including constructors. Check if the constructor or if there is some cover group that you want to check for. It's all as a data model, right? So you go and do it. And what we have done is in the PySlint, we provide you a minimalist set of rules available as case studies. So these are intended to give you motivation, to trigger your interest to build something more robust for your own requirements. So we help customers build on top of it. They have their own rules. They necessarily not always open it up to the public. So they could be proprietary rules, right? And so you can also customize existing rules. And you can build newer analysis tools or apps, which I'll show you towards the end of this presentation, what some of the customers are trying to do with it, right? However, this is not intended as a traditional electronics design automation tool, right, as a product. So rather, it's an open room for innovation, and we can build both qualitative and quantitative metrics, which is something unique in the lint space. So again, I'll show you some examples of what we do. So very high level before we jump into some case studies. So PySlint can be broadly talked about in two forms. One is the qualitative part, other is the quantitative part. In the qualitative, typically you get these coding styles such as, you want to make sure your classes are named some way, your drivers have a specific naming conventions, etc., assertions have a label, etc., right? There could be functional issues that you want to detect. You also have these reuse checks. For example, the UVM is active is a good example of how you want to keep your agents reusable. Right? On the quantitative side, you could build things like assertion density, coverage density. For example, how many cover groups have you written? What kind of complexity is in your cover group that would eventually impact your coverage closure cycles, both positive and negative way. So given that it's an open source, we want to jump straight into what you can do with it. Again, all the code that I show you today are going to be available on the GitHub, either are already available or will be available very soon for free in open source. So in case of DPI, again, I want to show you some variants. So in DPI, there are two potential spec strings that you could put in the double quotes, what you put as import DPI or DPIC. And there are subtle differences. DPIC is the preferred way to do in IEEE 1800. If you want to know the history and geography of it, please go and read the LRM, which I have given you a screenshot over there. Though it's allowed to use DPI, it has impact, especially around the 2-state and 4-state packed arrays. You don't want to be messing up with this. Just stick to DPIC, you're happy. In fact, the newer tools may not even compile the DPI. So the newer system Verilog tools are not even required to implement the DPI, as in the DPI as a spec string. It's only mandated to implement the DPI-C. So you better want to fix it. It's really a 2-character fix, but the key is to know that you're doing something wrong, right? And PySlint would find it in about 2 seconds, if you will, right? That's really what we want to show you over there. Another good example on the DPI lint that you may want to build is you want to ensure only 2-state variables are passed between system Verilog and DPI, both ways, both the inputs, outputs, the return values, etc. Right. So very, very trivial example. One of this that comes from our training, straight from our training in the past. So DPI training, for example. On the left-hand side, you see a import DPIC, which is the spec string looks good. It's a context task, generate value in C. with output integer int address and output data. Right, the one that is highlighted, there's a subtle bug. So when you run it in the simulation, you would start seeing CVC C address is 0xb. Data, the C side comes and says that data is going to be hexadecimal 16. That looks good. However, when you print it from the SV side, if you have already known the bug, hold on, don't worry about it. It's again a lint. Let's have some fun to figure out. So the CVC SV, if you read the print carefully, C generated address 0xb, right, which is good, system Verilog. But then the data seems to be 0xz, right? Whereas the C side was thinking the value is hexadecimal 16. The system Verilog side just found a value of Z. Why is that? Fundamentally, if you go back to the code, you see that output data inadvertently we missed out declaring the data type. So what happened? In system Verilog, the default data type happens to be logic. Logic, please recall, is a 4-state value, and hence you saw the Z over there. So the main takeaway here is avoid 4-state variables across system Verilog and C boundary. And the simple reason is C has native support for 2-state. You don't have to think too hard, right? However, if you still insist you want to do it the right way using the SV logic, etc. Right? It's very easy to mess up and pay for the debug. Better to PySlint it. So a very close example on the violation side, you see that, for example, if you have a DPI with a return value in 4-state, there's a rule that goes and checks DPI functions shall use 2-state types in return value. Using 4-state type can lead to unnecessary complication on the C side, as C side does not naturally support it, the 4 value. Right. It's just an example of what you can do with it. You can do a lot more what you want to do. So here are some sample rules. On the top, you see a table with 2 columns. I'm going to focus on the second column. You can do naming style checks, such as your class shall have a prefix or a suffix, cover group shall have so and so the prefix, the assumptions, the assertions, the coverage prefix, etc. You can check all that. You can also get a little bit more fancier with assertions. Specifically, for example, you want to have the fail action block mentioned, and you don't want to use a pause action block, and make sure you have a label, you have an end label, etc. You can do all that. Similarly, for classes, there could be functionality. For example, missing cast you could detect. A method not being declared extern could present troubles later on, so you want to kind of make sure these are adhered to. Nothing rocket science about it, but again, all this is today doable with open source is the big deal. Similarly, jumping guns on the UVM lint. If you're missing the override on your REQ parameter on the UVM driver, it might compile, but it will lead into other issues. So that's something you can again detect using the PySlint framework. UVM agent, if you do not use the isActive to check inside your build phase, we can catch it, because you remember that the driver and sequencer will be present only for active agents and not for passive agents. And if you do, and this is kind of the intention of the UVM, but if you don't code it the right way with a check on the UVM isActive field, then you're going to have a problem. Your subsystem guy, when he or she integrates your VIP or a UBC, is going to find that it's not really working even if I configure it as passive. That's something that's going to be a trouble. So you can again find that much early while you're developing your code using PySlint. Similarly, you don't want to be hiding the isActive. It's already declared in the UVM agent. You better use it. Monitor missing a VIF, for example, virtual interface. Something can be found right away. So here is another case study. We have a nice blog on it. If you want to take a look, it's aswego.blogspot.com. If isActive is redeclared, you're going to have a trouble. So in the line number 20, you see that somebody has in the class HBus master agent, which is extending from UVM agent, the isActive field is being redeclared. And we have a bunch of reasons as to why you don't want to do that. Right. So another nice, interesting example is system Verilog constraint distribution. If you remember the constraints in system Verilog distribution, it allows 2 forms of dist, right? Especially when it comes to range. One is called colon equals, other is called colon slash. It's not my intention to do a full-fledged training on what is each syntax really mean and what it really empowers you to do. You're welcome to take about training or read the LRM in detail, which is in this particular slide on the top right corner. You see that the colon equals operator assigns the specified weight to the item, or if the item is a range, to every value in the range. Now back to the top left corner, you see the 32 colon 65535, which is about 65,000 values. Each of them, you said the weight is going to be 1. Pardon me, right? So if you did that, what you've inadvertently done is 65,000 values, you've just given the same weightage. So if you run this random generator, you're going to find that the values are always greater than 32, most of the time at least, which is most likely not what you wanted. And by the way, this example came from one of the questions on Stack Overflow. And we jumped on that opportunity. We said, okay, this looks very interesting. Let's build a PySlint rule. It took what? An hour? So something like that. And now you have a nice rule over there. It says, maybe, you know what, the range is large and you're using a colon equals, maybe you wanted colon slash. Again, this is just an indication. Static checking is all about predicting what could go wrong. If you really wanted it, go ahead and disable this rule specifically and then go with it. But most of the time, you do not want the colon equals there, you wanted a colon slash. Just to conclude, before we wrap up this presentation, let's talk about quantitative analysis. Now, all this qualitative analysis is great. By the way, this is just a subset. What I just showed you, you can do a lot more than that. Due to the time constraint, we're going to restrict what we are talking today. The quantitative analysis, what you could do with system verilog test benches. For example, you could go and analyze how complex is the constraint model, because this could give you a hint as to what kind of constraint solvers would you need. There are 4 designs that are mapped over there on the left hand side, the constraint model. You could say that, okay, this particular block has more constraint than the other one, and hence may need more time in the constraint solving. Right? It could be over constraint, under constraint, etc. You can find all kinds of analysis. This particular slide is loved by managers because they get really a good quantifiable information on the team's productivity, the code, etc. Right? So you could also build on assertions, which is what you see in the center, the number of sequences, number of properties, number of asserts, assumes, and cover. Right? So this is very likely an example of a formal verification test bench wherein you had enough number of assumes, asserts, and covers. Right? So which is kind of giving you a hint that this test bench, this assertion test is actually a very nice formal friendly test bench, most likely. Similarly, functional coverage. You're mapping now the number of items or the cover points as well as the crosses. The more the crosses, the more number of cycles you're going to spend in doing coverage closure. Again, it's a good thing and a bad thing. It's up to you how you look at it. If the coverage model is very strong, which also indicates that your coverage, coverage specification was good, your verification plan was excellent, and hence you're going to spend more time doing the coverage closure. Right? So just be aware that the more you ask for in your coverage model, the more time you're going to spend in the execution, which is not necessarily a bad thing, but just be aware. And all this can be done by PySlint very statically. You don't have to really run through, let's say, 2-3 weeks of coverage regression to figure out that there was a problem with your coverage model to begin with. That's something you could actually lint it today and figure out what you want to do with it. That's kind of our summary for today. We are quite excited in what we are talking about. It's quite exciting new frontiers that we see. And open source, for once, has in system verilog domain a way to lead the commercial tools, right? Than just playing a catch-up game. Of course, to begin with, it's open source. That itself is a great interest. But we also have new rules that probably are hitherto unheard of, right? Or maybe it's there in, somewhere hidden out there. Unless you pay $1 million, you may not even get to see the rules. But over here, you get all the rules for free, whatever is implemented. And you also get a framework of implementing your own rules, customize them, etc. And it's a faster turnaround time. For example, some of the rules that I showed you have been done over, let's say, a couple of hours. Right? Yeah, of course, each rule, each capability could differ. Right? And it's potentially vast set of developers. Again, this is another great thing about open source, meaning once you start building on open source, you can choose the kind of developers that you want and the time. Whereas that's something you can hardly pick up in your commercial tools, right? Again, in test bench linting, this is greatly needed because there are not very agreed upon rules out there. So it's extremely important to have this vast set of developers. And we hope that a lot of engineers across the globe would pick up PySlint and write their own rules. So it's an invitation, open invitation to innovate. What would you want to build on top of this? Thank you very much. Again, reach out to us at asvigo.com. We'll be happy to help you build your own linters. Thank you. Take care.